In this short video, I will explain why 2's complement has been widely used in modern computers to represent signed integers. This number wheel lists 5-bit 2's complement integers. Positive numbers and 0 are simply represented as themselves. Negative numbers are represented in this way. Invert every bit of its positive equivalent, and then add 1. For example, suppose we want to find out how to represent -3 and 2's complement. First of all, we translate +3 to binary. In the first step, we flip every bit. In the second step, we add 1. The final result is 1, 1, 1, 0, 1, which is the 2's complement representation of -3. Why do we use 2's complement? One of the advantages is that 2's complement can simplify the hardware implementation of arithmetic functions. For addition or subtraction in 2's complement, the hardware can ignore the sign of operands if signed integers are represented. For multiplication, the multiplication hardware can also ignore the sign of operands if the product is required to keep the same number of bits as operands. This property simplifies the hardware design for addition, subtraction and multiplication. Note that this property does not hold true for division. We will use a very simple example to show that the hardware adder for adding unsigned numbers also works correctly for adding signed numbers. Suppose we are adding -9 and 6. These two signed numbers are represented in 2's complement in computers. Specifically, we can obtain the 2's complement representation of -9 by flipping all bits and adding 1. The 2's complement of a positive number is itself. Let's see what will happen if the hardware treats these two inputs as unsigned numbers. If these binary bits represent unsigned numbers, they are 23 and 6, respectively. Therefore, the hardware adds 23 and 6, and produces 29, in decimal, or 1, 1, 1, 0, 1, in binary. If the output represents a signed integer in 2's complement, it actually represents -3. This can be proved by inverting all the bits and adding 1. The result, -3, is exactly the sum of the original signed inputs. This example shows that, without any modification, the hardware adder designed for adding unsigned numbers works correctly for adding signed numbers. Similarly, the same subtraction hardware works correctly for both signed and unsigned subtraction, even though the sign of input operands is not examined. This example subtracts 6 from -9. The hardware ignores the sign of the inputs, and subtracts 6 from 23. The result is 17, in decimal, or 1, 0, 0, 0, 1, in binary. If the result represents a signed integer in 2's complement, then the result is -15. This is exactly the result of subtracting the original signed integers. Please visit the book website for more tutorials and examples.